Hello everyone, in this video we're going to explore topic 10.9 determining absolute or conditional convergence. Alright, when analyzing the convergence or divergence of a series A sub n, there are three possible cases. Case number 1, the series converges absolutely. How do we do it? We're going to check the series absolute value of A sub n to see if it converges. If it converges, then the original series also converges. Case number 2. Converges conditionally. If the series of absolute value of A sub n diverges, but the original series A sub n converges, then the original series A sub n is said to converge conditionally. Number 3. Diverges. If both series absolute value of A sub n and original A sub n diverge, then original A sub n diverges. Now note that the converse of the first case right here is not true. That said, the statement say if the series A sub n converges, then the series absolute value of A sub n also converges is not true. So keep that in mind. Alright. You don't have the converse for this one. Right? Now, example number 1. Determine whether each of the series is absolutely convergent, conditionally convergent, or divergent. Alright. Question A. Now, step number 1, we're going to check the series of absolute value of A sub n, right? So it's going to be, check the absolute value of this one. It's actually the series of 1 over n, right? Now, this guy is the harmonic series, so it's going to be diverges. Now, we're going to check the second one, original series, right? We look at this one. If this one diverges, case number 2, right? We're gonna check original one to see if it converges or diverges, right? If it converges, and then this is gonna be convergent conditionally, right? So original one is gonna be A sub n equals -1 raised to the n plus 1 over n. We look at this one, we see that -1 raised to the n plus 1, actually we're going to use the alternating series test, right? So we're going to let b sub n be 1 over n, right? So here's the alternating series test, right? We need to check to see if limit of b sub n equals 0. Second one, the sequence b sub n is a decreasing sequence, right? So we're going to use this one right here. And we have the tips to verify non-increasing behavior for a sequence using one of this one right here, right? So I'm gonna find the limit of 1 over n when n approaches infinity. This guy actually 0, right? So the first condition is met, right? Now second condition, I have b sub n plus 1 over b sub n equals 1 over n plus 1 over 1 over n, right? So it's going to be 1 over n plus 1 times n over 1, right? So it's going to be n over n plus 1, right? Less than 1, right? So the sequence b sub n decreasing, right? So then by alternating series test, this guy right here converges, right? So by number 2 right here, this series converges conditionally, right? Now question B, we're going to check to see if the series of absolute value of A sub n converges or diverges, right? So it's going to be 1 over square root of n, right? So it's going to be 1 over n power of 1/2, right? And this series diverges by the p series, right? Because p equals 1/2 less than or equal to 1, right? Now we're gonna check the original one, right? So we have the series of a sub n equals the series of -1 raised to the n over square root of n, right? Now we're gonna use the alternating series test to do this one. So we're gonna let b sub n equals 1 over square root of n, right? Now we're gonna take the limit of b sub n, right? When n approaches infinity equals limit of 1 over square root of n is going to be n power of 1/2, right? When n approaches infinity, it's going to be 0. So the first condition is met, right? Now we're going to move on to second condition, right? So we're going to take the b sub n plus 1 over b sub n. It's going to be 1 over square root of n plus 1 times square root of n over 1, right? So it's going to be square root of n over n plus 1. And it's going to be less than 1 for sure, right? Then by the alternating series test, the original one right here convergent. So you can conclude that the original one right here converges conditionally, right? Now question C. You need to check the series of absolute value of a sub n, right? So it's going to be the series of n factorial over 2 to the n, right? The factorial function always grows faster than the exponential function, right? So this series approaches infinity, which diverges, right? By the n-term test. Now we're going to check the original one. Now we're going to use the ratio test to check this one, right? The ratio test right here. So we're going to have the series of a sub n plus 1 equals. So you're going to take the limit of absolute value of a sub n plus 1 over a sub n when n approaches infinity equals limit when n approaches infinity of absolute value of times the reciprocal of this one, so it could be 2 to the n over -1 raised to the n times n factorial, right? Now we're going to simplify this one. -1 raised to the n plus 1 is going to be -1 raised to the n times -1, right? And then this guy and this guy cancel out, right? 2 to the n plus 1 is going to be 2 to the n times 2. This guy cancel out, right? N plus 1 factorial is going to be n plus 1 times n factorial, right? This guy cancel out, right? Now absolute value of -1 is going to be 1, right? So we don't really care about this one anymore, right? So the top equals, so we have limit when n approaches infinity, absolute value of n plus 1, right? Over 2, right? Now when n approaches infinity, this guy approaches infinity, right? So by the ratio test, the series diverges, right? And finally, the original one right here diverges, right? Now let's take a look at question D. We need to check the series of absolute value of a sub n, right? So it's going to be the series of 1 over n factorial, right? Now we're going to use the ratio test, right? So we have a sub n plus 1 equals 1 over n plus 1 factorial, right? So we have limit of absolute value of a sub n plus 1 over a sub n when n approaches infinity equals limit of absolute value of 1 over n plus 1 factorial multiplied by this reciprocal, right? So it could be n factorial over 1, right? when n approaches infinity. So it's going to be limit of n factorial over n plus 1 altogether factorial when n approaches infinity, right? So it's going to be limit of absolute value of 1 over n plus 1, right? When n approaches infinity. So this one equals 0, right? So by the ratio test, if the limit less than 1, the series converges absolutely, right? And we look at the number 1 right here. If this guy converges, and then original one must be convergent, right? Now, you have two different ways to deal with this topic. You either start with the original one, or you're going to start with the absolute value 1, right? Now, for the first one, the series a sub n either converges or diverges. If it diverges, you stop, right? If it converges, you're going to check to see if it is absolutely converges or conditionally converges, right? Number 2, you can start with the absolute value of the series, right? If it diverges, and then you're going to check to see if the original one is conditionally convergent or divergent, right? If it converges, and then you stop, because if this guy converges, and then original one must be convergent, right? Let's move on to example number 2. Determine whether each of the series is absolutely convergent, conditionally convergent, or divergent, right? Now question A, we're going to check the series of absolute value of a sub n, right? So it's going to be the series of square root of n over n squared plus 1, right? Now I'm going to use the direct comparison test. So I'm going to compare this guy with the series of square root of n over n squared, right? So I'm going to start with n squared always less than or equal to n squared plus 1, right? And then I'm going to take reciprocal both sides, so it could be 1 over n squared greater than or equal to 1 over n squared plus 1, right? So I'm going to multiply both sides by square root of n, right? So square root of n over n squared greater than or equal to square root of n over n squared plus 1, right? Now, this guy right here is larger, right? This guy right here is smaller, right? Now, we need to check this guy. So we have the series right here, right? It's going to be the series of 1 over n power of 3.5, right? And this guy actually converges by p series because p equals 3.5 greater than 1, right? So the larger converges, then the smaller must converge. And the original one right here converges, right? Because I just used the direct comparison test, right? And the first one right here, the series of absolute value of a sub n converges, then original one converges. We don't need to check the original one anymore, right? Now question B. I'm gonna check the series of absolute value of a sub n, right? So when you take absolute value of this one, it turns out to be the series of 2 to the k over k squared, right? Now I'm going to use the n-term test to check to see if this one is converges or diverges, right? Look at the n-term test right here. If the limit not equal to 0, the series diverges, right? So I'm going to take the limit of this one. When k approaches infinity, The top is the exponential function. The bottom is the polynomial function. The exponential function grows faster than the polynomial function, right? So this one approaches infinity, right? So by the n-term test, this guy diverges, right? Now I look at this one right here. Since it diverges, I need to check the original one right here to see if it converges conditionally, right? So I'm going to use the ratio test, right? So I have limit of absolute value of a sub n plus 1 over a sub n when n approaches infinity, right? It's going to be limit of a sub n plus 1. So it can be absolute value of -1 raised to the k plus 2, right? Times 2 to the k plus 1, right? Over k plus 1 square, right? Times this one reciprocal, so it can be k square over -1 raised to the k plus 1 times 2 to the k, right? When k approaches infinity, right? Now, since I use the variable k, so every single thing right here must be k, right? And -1 raised to the k plus 1 cancel out. So you have -1 power of 1. So if you take absolute value, it's going to be positive, so it's gone, right? Now, 2 to the k plus 1 and 2 to the k cancel out. So you have 2 on the top left, right? So you have limit when k approaches infinity of absolute value of 2 k squared over k plus 1 altogether square. Now when k approaches infinity, number 1 right here doesn't really matter, right? So it turns out to be limit of 2k squared over k squared. When k approaches infinity, it's going to be 2, right? So we look at the ratio test. If it's greater than 1, the series diverges, right? So you can say that this guy right here diverges, right? By the ratio test. Let's move on to question C. We're gonna check the series of absolute value of a sub n, right? So if you check absolute value of this one, it's gonna be 1, right? So it's gonna be the series of 1 over n, right? Now this guy actually harmonic series or the p series where p equals 1, right? So this one diverges by the harmonic series. Now we need to check the series a sub n. Now I'm going to use the alternating series test, right? So I'm going to let b sub n equals 1 over n, right? Now I'm going to check limit of 1 over n when n approaches infinity. This one equals 0. So the first condition is met, right? Second one, I'm going to check b sub n plus 1 over b sub n. It's going to be 1 over n plus 1 times this one reciprocal. It's going to be n over 1, right? So it could be n over n plus 1. This guy less than 1. It tells us that b sub n is decreasing, right? So the second condition is met, right? So we look at the alternating series test right here. Two conditions are met, the series converges, right? So then you can say that a sub n converges by the alternating series test. Alright, so you can conclude that the original one right here converges conditionally, right? Now let's move on to question D. We need to check the series of absolute value of a sub n, right? So if you check absolute value of this one, it's going to be the series of 1 over n squared, right? So this series converges by P series, right? So you can conclude that the original one, series A sub n, converges absolutely, right? Now let's move on to question E. We need to check the series of absolute value of A sub n, right? So it could be, now when n approaches infinity, nq should be positive, right? So I have the series of nq on the bottom. This guy is still inside the absolute value sign, right? Now observe that sine n always greater than or equal to -1 less than 1. So then the absolute value of sine n always less than or equal to 1, right? So then I'm going to divide both sides by n cubed. So I have absolute value of sine n over n cubed less than or equal to 1 over n cubed, right? So this guy is the same thing as, observe that this series converges by the P series, right? So this one converges by the direct comparison test, right? Now since the series of absolute value of A sub n converges, the original one right here converges absolutely, right? Now let's move on to question F. First, note that the terms are non-negative, since 1 plus cosine n greater than or equal to 0, right? Now observe that this series right here converges by P series because P equals 2 greater than 1. Now for the second one right here, I'm going to check the series of absolute value of cosine n over n squared when n goes from 1 to infinity, right? It's going to be absolute value of cosine n over n squared when n goes from 1 to infinity, right? Now you know that absolute value of cosine n always less than or equal to 1, right? So this guy less than or equal to the series of 1 over n squared, right? But this one converges by P series since P equals 2 greater than 1, right? So by direct comparison test, this guy converges, right? Since this guy converges, then the series n goes from 1 to infinity of cosine of n over n squared converges, right? Now this guy converges. This guy also converges. Then the original one right here must converge, right? Now let's move on to the next one. Rearrangement of series. A finite sum such that 1 plus 3 minus 2 plus 5 minus 4 can be rearranged without changing the value of the sum. However, it's not necessarily true of an infinite series. It depends on whether the series is absolutely convergent or conditionally convergent. Alright, so let's take a look at example number 3. It has been proved that the alternating harmonic series converges to Ln2. Now, rearrange the series to produce a different sum. We're gonna rewrite this one as 1 divided by 1 is gonna be 1 minus 1 half, right? And then subtract 1 over 4 plus 1 over 3. Subtract 1 over 6 minus 1 over 8 plus 1 over 5 minus 1 over 10 minus 1 over 12 plus 1 over 7 minus 1 over 14, right? Plus etc., right? Now I'm going to group the first two terms, right? The next two terms right here. This guy and this guy, this guy and this guy, right? So 1 minus 1 half is going to be 1 half minus 1 over 4 plus 1 over 6 minus 1 over 8 plus 1 over 10 minus 1 over 12 plus 1 over 14 plus etc. Right? Now I'm a factor 1 half out, so it will be 1 half times 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5 minus 1 over 6 plus 1 over 7 minus etc. Right? This guy actually ln2, right? So it will be 1 over 2 times ln2, right? Now let's move on to example number 4. For what value of s is the series absolutely convergent? So if this one is absolutely convergent, we have this series must be convergent, right? So we're going to use the ratio test. So we have limit of absolute value of a sub n plus 1 over a sub n when n approaches infinity, right? This one right here is a sub n now. Limit when n approaches infinity of absolute value of a sub n plus 1 is going to be n plus 1 times s plus 5 raised to the n plus 1 over 7 raised to the n plus 1, right? Multiplied by this one reciprocal, so it could be 7 raised to the n over n times s plus 5 raised to the n, right? Now we're going to simplify, so it could be limit when n approaches infinity absolute value of. Now on the top n plus 1, the bottom is n, we just rewrite, right? Now this one s plus 5 raised to the n plus 1 can be written as s plus 5 raised to the n times s plus 5, right? So this guy and this guy cancel out, so we have s plus 5 left on the top, right? Now 7 to the n and 7 to the n plus 1 is going to be 7 left on the bottom, right? When n approaches infinity, this guy right here approaches 1, right? So we only have s plus 5 over 7 left, right? And we need this guy s plus 5 over 7 less than 1, right? By ratio test right here. Be the same thing as s plus 5 over 7 less than 1 greater than negative 1, right? So it's going to be s plus 5 less than 7 greater than negative 7, right? Subtract 5 both sides, so it's going to be negative 12 less than s less than 2, right? So the answer must be D. Now if the question asks you to find the value of s, show that the series is conditionally convergent, and then you need to check the endpoint. We need to check s equals negative 12, s equals 2, right? And then we're going to do this in this problem B right here, right? Problem B, we do exactly the same thing, right? We're going to use the ratio test, right? So we have limit of a sub n plus 1 is going to be n plus 1 times s to the n plus 1 over 4 to the n plus 1 times n plus 1 altogether square plus 1, right? Times this reciprocal. So it could be 4 to the n times n square plus 1 over n times s to the n when n approaches infinity, right? Now we're going to simplify this one, so it could be limit of absolute value of n plus 1 rewrite, right? And right here we just rewrite, right? S to the n plus 1 and s to the n is going to be s on the top left, right? Now 4 to the n plus 1 and 4 to the n right here, we have 4 left on the bottom, right? Now on the top we have n square plus 1. The bottom we have n square plus 2 and plus 2, right? When I expand this one and simplify. Now, when n approaches infinity, this guy approaches 1. This guy approaches 1, right? We have s over 4 left, right? So we need this one less than 1, right? By ratio test. So we have absolute value of s over 4 less than 1, right? So it's going to be s over 4 less than 1 greater than negative 1, right? So it's going to be s less than 4 greater than negative 4, right? This guy is the absolutely convergent, right? But the question asks us to find the conditionally convergent, right? So we need to check the endpoints, right? So we need to check s equals negative 4 first, right? Today over here, we have the series n goes from 1 to infinity of n times negative 4 to the n over 4 to the n times n squared plus 1, right? So it's going to be the series when n goes from 1 to infinity of n times 4 to the n times negative 1 to the n, right? Over 4 to the n times n squared plus 1, right? So then you can cancel out this guy and this guy, right? So then it's gonna be the series when n goes from 1 to infinity of negative 1 raised to the n times n over n squared plus 1, right? Now I'm gonna let b sub n be n over n squared plus 1, right? So I'm going to use the alternating series test, right? So I'm going to take limit of b sub n when n approaches infinity. It's going to be this guy actually 0, right? So we'll look at the alternating series test right here. The first condition is matched, right? Now we're going to check the second condition to see if the sequence is decreasing, right? I'm going to let f of s equals s over s squared plus 1, right? This guy right here. The domain s greater than equal to 1, right? Look at this one right here. So I'm going to check the derivative of this one. I'm going to use quotient rule, right? So it could be negative 2 s squared plus s squared plus 1 over s squared plus 1 all together squared, right? So it could be negative s squared plus 1 over s squared plus 1 all together squared. The bottom always positive, right? The top is less than equal to 0 because s greater than equal to 1, right? So then you have f prime of s less than equal to 0. Then f of s is decreasing, right? Alright, so using the alternating series test, the first and the second condition satisfies. So then the series converges, right? So s equals negative 4 works, right? And the answer is B. Now we're going to check to see if s equals 4 works, right? Now if s equals 4, we have s equals 4 right here, right? So I just change the sign right here, right? So then I don't have this guy, right? So I only end up with the series of n over n squared plus 1, right? I don't need this guy, right? When n goes from 1 to infinity, right? Now we need to compare this guy n over n squared plus 1 with harmonic series, right? Why? Because this guy is the same thing as n over n squared. When n approaches infinity, you can drop 1, right? And you can simplify it's going to be 1 over n, right? This one is harmonic series. Harmonic series always diverges, right? So now we're going to use the limit comparison test, right? So we have limit when n approaches infinity of a sub n over b sub n. Now this one right here is a sub n. This one right here is b sub n, right? So we have limit of absolute value of n over n squared plus 1 divided by b sub n, which means multiplied by its reciprocal, right? So it could be n over 1 when n approaches infinity, right? So then it's gonna be limit when n approaches infinity. This guy always positive, right? So I can remove the absolute value side, right? So it could be n squared over n squared plus 1, right? When n approaches infinity, you can drop 1 by relative growth rate, right? So we have limit when n approaches infinity of n squared over n squared, right? So it could be 1. This one is the positive number and finite. Limit comparison test right here. If we get the limit equals L, that is positive and finite, right? Now, you're going to check if one series converges, then both series converge, right? If one series diverges, then both series diverge, right? Now, since this one diverges, right? Original one right here must be divergent, right? So you can conclude that a sub n diverges by limit comparison test, right? So as for 4, it's going to be diverges, so this one is wrong, right? So the final answer must be s equal negative 4 only, right? Question C. Which of the following statements true about the series? Alright, so first we need to check the absolute value, right? So we have series of absolute value of this one, right? So it could be negative 1 to the n plus 1 over n power 1 third, right? When n goes from 1 to infinity, right? So this guy actually, the series when n goes from 1 to infinity of 1 over n power 1 third, right? And this one diverges by p series because p equals 1 third less than or equal to 1, right? So the absolute value of the series is divergent. We need to check to see original one is conditionally convergent, right? So we're going to use the alternating series test right here, right? So we're going to let b sub n be this guy right here, right? So we let b sub n equals 1 over n power 1 third, right? So we're going to take limit of b sub n is going to be 1 over n power 1 third. When n approaches infinity, it's going to be 0. So the first condition is matched, right? Now the second condition, we're going to check to see if this one increasing or decreasing, right? So we're going to use f of s equals 1 over s power 1 third, right? S greater than or equal to 1, right? Right here. So then f prime of s equals, we're going to use the quotient rule, right? So the derivative of this one equals 0 times this one is going to be 0 minus 1 over 3s 1 third subtract 1 is going to be negative 2 third, right? Over s power 2 third. So it's going to be negative 1 over 3 s power of 4 third, right? And this one always less than 0, right? So f of s is decreasing, right? And then the series b sub n decreasing. The second condition is matched, right? So you can conclude that this guy right here converges conditionally, right? So the answer must be A. Now let's move on to question D. We do exactly the same things, right? Now we need to check the absolute value, right? So we have series of absolute value of a sub n, right? It's going to be absolute value of -1 raised to the n over 1 plus n power of 3.5, right? So it's going to be the series of 1 over 1 plus n power of 3.5, right? We have 1 plus n power of 3.5 always greater than or equal to n power of 3.5, right? And we take reciprocal of this one, it's going to be 1 over 1 plus n raised to the 3.5 less than or equal to 1 over n power of 3.5, right? Now this one is the larger, right? This one is the smaller, right? Now the larger converges by p series, right? Since p equals 3 over 2 greater than 1, right? So since the larger converges, the smaller converges, right? By comparison test. Alright, so since the absolute value of this series converges, the series converges, right? So the answer must be B. Now let's move on to the last question, question E. Which of the following statement true about this series? Alright, so first we need to check this series of absolute value of a sub n, right? To see if it converges or diverges, right? So this guy is the same thing as series of L n of n over n, right? Because when you check absolute value of this guy, it's going to be positive, right? Now we're going to check this one, right? So observe that if n greater than e, right? And then ln of n greater than ln of e, right? So ln of n greater than 1, right? Divide both sides by n. So you have ln of n over n greater than 1 over n, right? We're going to use direct comparison test. So we know that the series 1 over n diverges by harmonic series test, right? So then by direct comparison test, the smaller diverges, the larger diverges, right? So then we look at this one, the smaller diverges. Then you can conclude that the series of ln of n when n goes from 1 to infinity diverges by direct comparison test. So we need to check the series -1 to the n ln of n over n when n goes from 1 to infinity, right? So we're gonna let b sub n equals ln of n over n, right? Now we need to use the alternating series test, which is right here, right? So we need to find the limit of b sub n, and then we need to prove that b sub n is decreasing, right? So I have limit of b sub n when n approaches infinity equals limit of ln of n over n, right? When n approaches infinity, indeterminate form, right? So we need to use large scale rule, right? So we have limit when n approaches infinity, derivative of ln is going to be 1 over n. Derivative of n is going to be 1, right? So when n approaches infinity, this one approaches 0, right? So the first condition is met, right? Now the second one, we need to prove that b sub n decreasing, right? So we're gonna let f of s equals ln of s over s, right? Now we're gonna take derivative of this one, so it could be f prime of s equals, we're gonna use the quotient rule, right? So derivative of ln s, it could be 1 over s times s minus derivative of s, it could be 1 times ln s over s squared, right? So we simplify, it's gonna be 1 minus ln s over s squared, right? The bottom is positive, right? So we need this one to be less than or equal to 0, right? In order for this one to be decreasing, right? So then we have 1 minus ln s less than or equal to 0, right? So then ln s greater than or equal to 1, right? So s greater than or equal to e power of 1, which means e, right? So we can conclude that f of s is decreasing for s greater than or equal to e. Is the same thing as the series b sub n is decreasing. So the second condition is met, right? It tells us that the series a sub n converges by alternating series tests, right? But you know that the absolute value 1 diverges, right? So the answer must be 3. The series converges conditionally, right? And it's good time to stop. Thank you for watching. I hope you enjoyed the video. Remember that if you failing to prepare, you're preparing to fail.
We rise like tall buildings as the chemicals they take us higher. The night's young, it has just begun as she puts her hand in mine.